All right, let's take a look at torque again. We saw that if we have, let's go ahead and get a good definition of this. Make an axis. If we had some force acting away from some rotation of origin, we'll call it O, then which way should I draw this? Put my force on here. There we go. So they're not perpendicular in this case. Just note that. This is acting at some angle. We'll call it phi. We saw before that we had a general definition for torque, but it was mainly our perpendicular case where the force either had to be perpendicular to R or we looked at the perpendicular distance to the force. And what does that mean again? Well, if this is some force F, we can do two things. We can project this distance R out and then look at the component perpendicular, right? Like that. So that's perpendicular now. Or we can take the force and trace it back until we find where the perpendicular is. So right about there. Either way would give us the same answer. But let's take a look a little bit deeper. Let's say, what about if it's a vector? Torque is a vector quantity, and it's equal to the position vector R, right here, crossed into this force F, which is now a vector. This reduced to the non-vector quantity torque is equal to Rf sine theta, or R sine theta F. We got both of those definitions in a different manner, right? One was the component of the force perpendicular to R, and one was the component of R perpendicular to the force. So that would be your R perpendicular, right? This is R perpendicular. This is the F perpendicular. Okay. In general, though, it can be 3 dimensions, and if we have some vector pointing off into space and some force acting on it, the vector R could have as many components, 2i plus 3j plus 4k, and the force could be as many components, up to 3, that we'd want also. -2 in the I direction, I'm just making this up, plus 3 in the y, and 4 in the k again. We can take the cross product of those, but we're typically not going to have to do 3x3s, and we're typically not going to have to even do 2x2s in here. So let me just show you a trick. We're generally going to be looking at things that move in a circular plane, in which we will very often know the radius of something. We can turn this radius into a vector, right? It's the magnitude of whatever the radius is, and that looks like it's in the positive I direction. Now, if we had a force acting on it, let's say, and this doesn't have to be a circle, that's just the motion. It could be some beam or something, and let's say we're going to apply a force. Well, that force is also a vector, and we can, it's perpendicular, so this could be maybe even a force down here from friction causing it to rotate or something. That's also in the I direction, right? What we're going to do is use this cross product definition. In this case, we'll say the force is equal to the magnitude of the force, and then it's in the positive j. And then what I do is this little trick. So you say I crossed into j gives you positive k. J crossed into k gives you positive I. And k crossed into I gives you positive j. And we can go the other way. We can say I crossed into k gives us a minus j. K crossed into j will give us a minus I. And j crossed into I will give us a minus k. So I recommend remembering that right there. That'll get you by about 90% of the time. So let's take a look. What's the torque then? The vector quantity of this. That would be R crossed into F. And now we can just do a simple cross product of R, which was R in the I direction, crossed into F in the J direction. And I crossed into J, come over to my table, I crossed into J gives me K. So it's in the positive K direction, and the magnitude is R times F. So what does that tell us? A positive K direction means it's going to rotate. Imagine your thumb sticking out of the computer screen and your fingers wrapping around this way. So your fingers are here wrapping, and your thumb is pointed up right here. If you wrap your fingers in the direction of the force about the rotation point, the direction your thumb sticks up, or the right hand rule, is going to tell you the direction of the rotation. And this is going to be a positive torque because we measure from the positive x-axis in the counterclockwise direction, right? Counterclockwise is negative. Okay, just don't forget that works for 2x2, that works for 3x3. We could have, let's say, some solid beam, uniform mass distribution, and it could have let's say it's floating in space, it's at rest. We could apply a force that looks like this, where it's equal to 2I plus maybe some 3J, right? And that's a vector. Well, if that is applied through the center, all that's going to do is cause it to translate. But if it's applied at some position, at some distance from our center of mass, we'd have to take the cross product. So that just goes a little bit deeper into torque. And if needed, you can always go to the cross product definition. And we're going to talk a little bit more about the cross product because the next topic is angular momentum. Talked about linear momentum before. Remember, momentum was mass times the vector velocity. We're just going to attach an R onto that thing, and we'll call it linear momentum instead. I'm sorry, angular momentum instead. So there's our definition. I'll show you how to get there and how to use it next time.